Selection sort is an algorithm that, as you might expect, sorts a set of elements. An algorithm, recall, is a step-by-step set of instructions for completing a task. In selection sort, the basic idea is this. Find the smallest unsorted element and add it to the end of the sorted list. Effectively, what this does is build a sorted list one element at a time. Breaking it down into pseudocode, we could state this algorithm as follows. Repeat this until no unsorted elements remain. Search through the unsorted data to find the smallest value. Then swap the smallest value with the first element of the unsorted part. It may help to visualize this, so let's take a look at this. So this, I contend, is an unsorted array, and I've indicated it by indicating that all of the elements are colored red. They are not yet sorted. This is the entire unsorted part of the array. So let's go through the steps of selection sort to sort this array. So again, we're going to repeat until no unsorted elements remain. We're going to search through the data to find the smallest value, and then swap that value with the first element of the unsorted part. Right now, again, the entire array is the unsorted part. All of the red elements are unsorted. So we search through and we find the smallest value. We start at the beginning, we go to the end, we find that the smallest value is 1. So that's part 1, and then part 2, swap that value with the first element of the unsorted part, or the first red element. In this case, that would be 5, so we swap 1 and 5. When we do this, we can visually see that we've moved the smallest valued element of the array to the very beginning, effectively sorting that element. And so we can indeed confirm and state that 1 is sorted. And so we'll indicate the sorted portion of our array by coloring it blue. Now we just repeat the process again. We search through the unsorted part of the array to find the smallest element. In this case, it's 2. We swap that with the first element of the unsorted part. In this case, 2 also happens to be the first element of the unsorted part. So we swap 2 with itself, which really just leaves 2 where it is, and it's sorted. Continuing on, we search through to find the smallest element. It's 3. We swap it with the first element, which is 5. And now 3 is sorted. We search through again. We find the smallest element is 4. We swap it with the first element of the unsorted part. And now 4 is sorted. We find that 5 is the smallest element. We swap it with the first element of the unsorted part. And now 5 is sorted. And then lastly, our unsorted part consists of just a single element. So we search through it. We find that 6 is the smallest and, in fact, only element. And then we can state that it is sorted. And now we've switched our array from being completely unsorted in red to completely sorted in blue using selection sort. So what's the worst case scenario here? Well, in the absolute worst case, we have to look over all of the elements of the array to find the smallest unsorted element. And we have to repeat this process n times, once for each element of the array, because we only, in this algorithm, sort one element at a time. What's the best case scenario? Well, it's exactly the same, right? We actually have to still step through every single element of the array in order to confirm that it is, in fact, the smallest element. So the worst case runtime, we have to repeat a process n times, once for each of n elements. In the best case scenario, we have to do the same. So thinking back to our computational complexity toolbox, what do you think is the worst case runtime for selection sort? And what do you think is the best case runtime for selection sort? Did you guess big O of n squared and big omega of n squared? You'd be right. Those are, in fact, the worst case and best case runtimes for selection sort. I'm Doug Lloyd. This is CS50.